Hi, I'm David Robinson, owner of Robinson Labs Limited in Stafford in the UK. In this video, I'm going to show you Webasto and some of the other controllers and people's solutions and why they might not be a good idea and how maybe our solutions are better for you. So I'll take you over to the computer.
Okay, so we're over at the computer now and we're looking at the analog to W bus converter on eBay. Now there are many things to point out on this board, why it's not marine compatible, why it's not a good idea to buy it. So here we go. The first thing is, as you can see, you have a solder blob there to select between parking heater and supplementary heater. So this already may require soldering skills. In a professional setting, that's not the best choice. Second, the board quality is absolutely disgusting. You can see how the tracks are laid out, that they have been done with the auto router. The quality of this board is the sort of board that if you went to repair it with a soldering iron, you'd start lifting tracks. It is of real poor quality. To give you an example, where you see the vias, the little interconnects through the board, you see that they don't even contain mask. As a matter of fact, they're not even plated. And then just moving down where you see the squiggle track that moves between the two holes, it's missing plating. It's missing mask and isn't plated. You can see that it's actually copper. So what happens in a salty sea air condition of marine? Well, these vias being copper only, as soon as they see salty sea air, I give that 12 months and they'll go green and blue and eat themselves through and break their own circuit. The pieces will literally drop off this board within 12 months. There's some major design flaws in this board also. I'll give you an overview of the board. So there's the main microcontroller, which I can't make out, but due to its pinnage is something similar to a tiny 44 or something equivalent. Definitely not automotive grade. The actual resonator used is not in a metal can, so it's susceptible to moisture damage and ingress. Then this is the main power regulator, which is some sort of SOIC 8 package, like a 7805. That is, well, at best can only supply 150 milliamps, which is probably enough to run this board, but it's not automotive rated. Will only have protection to 18 to 24 volts maximum. It's a bit weak for this particular application. You can see that this board isn't wave soldered, it's definitely hand soldered. If you view the two LEDs there on the left, you can see that both left solder joints are actually dry. They haven't wet to the board correctly at all. It's quite shoddy soldering, to be fair. So that's not the best bet. And then we move down, and here's where problems happen. We can see the negative connector there, which is absolutely horrible. You can see the exposed copper of the wire. Any exposed copper of wire, anybody on a sales ship knows, instantly goes green. If this is hidden somewhere in your car, salt spray in winter, it's going to go green, it's going to rot through, it's going to need repair. It's an okay termination for wiring on PCBs that live inside or inside an enclosure, but not really floating like this. Moving down the negative track, we can see two big diodes. That's fine. And then what these are is SOIC 8 package MOSFETs, which in our opinion are a little weak. At best they will supply 4 to 6 amps, which should be adequate to run a coolant pump and so on, but nevertheless they are still a little weak. Now here's a design fault. You see the left MOSFET, you see it's got a nice big track, and the track thickness matches the wire thickness. That's great. Same with the other MOSFET, it's got a nice big track, bit thicker than the other one, but matches the wire thickness. Not really an issue there. Well, how these MOSFETs work is the bottom 4 pins, as you can see on the left one's easier to see, is they're all bridged. Same with the right one, that they're exact identical packages. However, this is where the design fault is. They have nice big fat tracks out to carry the current. However, current is only supplied on pin 1, and as you can see, pin 1 is very, very thin off the main track, which means if you supply a bit too much power there, if it doesn't blow the MOSFET, it'll blow like a fuse. So there's a major design fault there. However, that's not the worst of it, funnily enough. Now it's been shown to you. Yeah, I would say only half of these wires, I mean, there's no words for the negative or the positive, and especially the W bus there. You can still see that in the soldering there is a little bit of copper that hasn't wicked up the wire, exposing copper. That copper will go green, it will rot out of the board. Incidentally, the worst part, the communication. This is the communication. That's all it is. It's 2 transistors in a push-pull arrangement with 2 diodes back to back. I will now show you the schematic of this part of the circuit and why it's absolutely terrible to use with a £200 circuit board in a Webasto. So we'll move to the schematic. Okay, this is that schematic of the output, and as you can see, 2 transistors here. Basically, this side is either your computer or the actual controller board, and then this side goes out to the Webasto. So there is a lot of room for error here. You have 2 12-volt feeds coming through 2 10k resistors. Now in a perfect world, when TX is sent, it clamps this, which is sort of like a Darlington pair, which then clamps the K line down to ground from 12 volts, and that's how it transmits. However, if this resistor burns out for any reason, it would send raw 12 volts straight on the K line, and the only other protection is this 10k resistor. However, if there is another module on your K line sending some data at the same time, it will also pull it to ground, which then could overthrow this and send voltage straight back into your computer or your controller board and really give you a bad day. So this is the cheapest, horriblest way to drive a K line. It's dangerous, there is no isolation, so if anything did go wrong, like this transistor shorts from collector to base, the emitter breaks inside or whatever, then yes, it will put 12 volts straight on TX line. So it's a disaster waiting to happen. So now you have seen the analog to W bus converter. Well, what you're not getting for what you're paying for. There is one other company at the minute, and I will show you that now. This is Oltox RU, a Russian. They have a W-bus converter in development, and apparently it's coming soon. It's very generic from how it's wrote. It's a bit Ringlish. It's a bit Ringlish. However, the data that we have on here, we can show you. They're very good at just naming and naming. And what I mean by that is anybody who's researched Webastos knows that this is the one we're trying to play with. We know that a Z and aftermarket systems start straight up with a 12-volt signal. This is the problem that has been required for the V. So they've just listed everything known to man. Also note the price tag. Now if we move on to the technical parameters that we can see, you see the supply voltage 10 to 18, well that's just shocking. Standby current less than 5 milliamp, well what is it? And the max current for auxiliary output terminal is only 150 milliamps. That's not quite enough to run some relays. It's very poor of an output. That is literally a pin on a microcontroller, so it would need a transistor before running a relay. So auxiliary work would have to be done to this. And then our operating temperature range is -40 to +85, so it doesn't have a military spec. I mean, our board carries -40 to +125. So with that sort of price tag, with that sort of information, I would say this one is definitely to steer clear from. And although Oltox is an actual professional company, what sort of warranty do you get? If you send your money to Russia, are you going to get it back? Definitely one to steer clear of. So, why is Robinson Labs equipment better? Well, let's give you some specs. So firstly, this is the data sheet for the PIC16F628A, which is an 18-pin flash-based 8-bit microcontroller with nanowatt technology. We can see that it operates up to 20 megahertz. We actually run ours at 18.432. Standby current is 100 nanoamps at 2 volts. So we're looking at about 120 microamps in use and standby. The operating current is excellent. There's 120 microamps. We move down. So we get to the electrical specifications and absolute maximum ratings. As you can see, the ambient temperature under bias is -40 to +125. Our VDD with respect to ground, it will tolerate 6.5 volts, which is quite respectable. Even maximum current sourced for port A and port B combined is 200 milliamps. So it's a much hardier chip. We'll move on to the ATtiny85. The ATtiny85, it's an automotive rated part as usual for this particular application. And well, there's not a lot to say about the ATtiny85, it is what it is. But as I say, in this application, all our microprocessors and chips are all automotive rated. Just makes sense. We'll now move on to the piece of the resistance, the monolithic bus driver. Okay, so rather than using two horrible little transistors as an arrangement to pull K-line down, we use a standalone monolithic bus driver with ISO 9141 interface. If you were to take your Webasto apart and look on the circuit board, you will find that it has a LIN bus driver chip or an ISO 9141 chip. So why would you want to attempt to talk to that chip with two horrible transistors when it should be another one of these chips talking to it? That just makes sense. So when you look at this, you can see the operating power supply voltage range, obviously 4.5 VS, up to 36 volts and 40 volts for transients. It's even got reverse supply battery protected down to minus 24 volts, low mode with very low consumption, 1 milliamp. Low quiescent current in off condition is 120 microamps. What that means is these boards can be left connected to your battery, to your car, to your boat. It's not even the amount of an LED, so it's not going to run the battery down at all. These can be fitted and left there permanently. Also, the K-line output current limitation at 60 milliamps. It's defined off in the output status in an undervoltage condition, and if there's a voltage or ground interruption, it will self-terminate. These things are very stable and made just for the job. We move down a little. When we have a look at the block diagram, you actually see from the K-line to the TX and RX actually uses a comparator. But these comparators are then output to input with MOSFETs with overprotection. The overprotection is clamp Zener diodes. So this whole thing has its own protection and reverse protection built in on every input. It's a very solid, very hardy device built to do just this job. I'll now show you an application circuit for this. So here's the application circuit for the 9637D, and you'll note straight away that if we halve the chip in the middle, that your computer or your controller board sits this side always, and 12 volts with reverse protection sits this side. So there is absolutely no way that 12 volts on the K-line could get back to your computer. This is isolated. So a much better design. It's built for the job. It's not two nasty transistors doing the work. And also on the blue VAG KKL leads, when we go back to the data sheet and we see the two comparators, well, these are comparators built in. See, this comparator compares at 1.75 volts on the TX to stabilize through VCC. So it measures VCC, has a reference, and is very stable. In the VAG KKL lead, they use an LM339, which is a quad package comparator. So they're using a standard comparator to do this job without all the added extra protection and sourcing and syncing. Very nasty. So we'll move on now to a few shots of our boards, because as I say, we do not have them here for another couple of days, and then they will be built up. And on the extension of this video, if you subscribe, you'll get the video. Then when you see the next video, they'll be for sale on eBay. I'll show you the controller now. Okay, so this is our board. It's all shot in gold for corrosion protection. It has the best quality mask and uses the best FR04 available. As you can see, it has pullback and a full copper pore ground plane. This is for electromagnetic interference. As you can see, we have screw terminals. We have two dedicated 7805 voltage regulators, or 78M05 voltage regulators. We have our Tiny 85 watchdog. We have our main PIC16F. And we have our ISO 9141 dedicated driver chip. Here is an IRL B3034 PBF high power MOSFET. Its capability is 195 amp package limited. The silicon limit is 343 amps, but in the TO220 package it's limited to 195 amps. Basically because any more you'd melt the legs off it. So plenty of headroom, no problem there. The track from it has been calculated with the width to allow 25 amps. The screw terminal is rated at 16 amps, so there is plenty of headroom here. Our vias, when the board is built up, are all filled with solder, so they become a solid peg through the board. This is for vibration resistance. Extra things to note are extra vias shot under the power transistor, well, the MOSFET and the voltage regulators. This is to help with heat should there be any, which there shouldn't. Under all the silkscreen is copper embossment, so should any of the silkscreen get scratched off, rub off, a mishap, the embossment in copper will always remain under the mask. So there is no way to lose what connectors are what. Once our boards are made up and tested, they are then dipped in a topicalizing solution or a varnish, so it totally seals the board from moisture, corrosion. Very high quality. I'll now show you the replacement for the KKL. Here is our replacement for the KKL to be used with the Webasto software. Yet again, board, best money can buy. Copper ground plane for EMI interference. Shot in gold. Screw terminal. 12 volts W bus ground. We have our dedicated ISO 9141 driver. We have an FT232RL USB to serial. We've broke out the TX and RX lights so you can see the communication protocol happening. We have stability capacitors, various protections, and the USB is a mini USB, not a micro USB. The reason for this is the mini USB is seen as the industry standard and is much stronger than a micro USB that's a little weak. So this would be your replacement for your KKL. This can be fitted permanently, leaving a USB connector that you can connect to at any time. I'll now show you a KKL lead. Here somebody has made up a KKL lead. Here's the inside shot. We find that disgusting. So you can see a CH340 rather than an FTDI. And this was built 3rd of the 3rd 14. That's just amazing. Here is your LM339, and as you can tell, there's absolutely no protection. So I'll show you the application circuit for this. Here's the schematic for the lead. So you have the USB CH340, and then it uses the LM339, which is a quad op amp, to do the KKL switching, it's not the best at all. There is absolutely no protections. Should there be a spike and this outputs incorrectly, or the comparator goes wrong, it will push 12 volts to the CH340. The CH340 has no protection like the FT232RL, so it could in fact blow the CH340, backfeed into USB and damage your computer. This is why this method is not recommended.